In this lecture, we will be studying more about how do we design an intelligent agent. So, if we want to design an intelligent agent, we must know what's an intelligent agent. So, here, definition is given: an intelligent agent perceives its environment via sensors and acts rationally upon the environment with its effectors. A discrete agent receives percepts one at a time and maps this percept sequence to a sequence of discrete actions. An intelligent agent understands more about the environment via sensors and acts accordingly with the effectors with the help of understanding about the environment. So, an intelligent agent have the following properties. It must be autonomous, it must be reactive to the environment, must be proactive, that is, it is goal-oriented, and it interacts with other agents via the environment. A system which is autonomous or can perform its own actions is an intelligent system, and that is reactive to the environment, that can act accordingly to the difference in the environment, is an intelligent system, and it's an goal-oriented system is also an intelligent system, and those systems that can interact with other agents in the environment is also an intelligent system. Here a diagram is given where environment is provided and an agent is provided. An agent has a sensor and it's also have effectors. Its action is performed through effectors while the sensors provides the percepts from the environment. Then we will be discussing more about sensors and effectors. So, what do we mean by sensors or percepts and effectors or actions? Let's take the case of humans. There are sensors such as eyes, ears, skin, tongue, nose, and neuromuscular system, while in case of persons, there is, at the lowest level, electrical signals from these sensors as well as after pre-processing objects in the visual field, location, textures, colors, etc., auditory streams, pitch, loudness, direction, etc. Effectors are limbs, digits, eye, tongue, etc. The actions involved are lifting a finger, turning left, walk, run, carry an object, etc. The point here is percepts and actions need to be carefully defined, possibly at different levels of abstraction. So in the next slide, we will be looking about an example. Here, an example is given for intelligent agent, that is automated taxi driving system. Here we will have percepts, actions, goals, environment, etc. So here percepts include video, sonar, speedometer, odometer, engines, sensors, keyboard input, microphones, GPS. And for actions, it includes steer, accelerate, brake, horn, speak, and display. Goals include maintaining a safety, reach destination, maximize profit, that is, reduce fuel, tire wear, etc., obey laws, then provide passenger comfort. The environment that is used here is US urban street, freeways, traffic, pedestrians, weather, customer. Different aspects of driving may require different types of agent programs. Here it states that different types of automated taxi driving end system changes according to the change in environment. That is, we can't use this automated taxi driving system in another place. It is specifically used, it can only be specifically used in this conditions, that is US urban street, freeways, traffic, pedestrian, weather, and customers. In this session, we will be talking about rationality. An ideal rational agent should, for each possible percept sequence, do whatever action that will maximize its expected performance measure based on the percept sequence and its built-in and acquired knowledge, which means for any task that is provided by using the percept sequence and the acquired knowledge that is already built in, it will maximize the performance. And the next point is rationality include information gathering, not rational ignorance. If you don't know something, find out. That is in this case here information gathering occurs. If the system doesn't know something, what will it do? It tries to find out the answer for it or the solution for it. Rationality need a performance measure to say how well a task has been achieved. Here a performance measure is used so as to analyze where the task achievement is acquired or not. Types of performance measure. There are certain types of measures to look at whether the rationality has completed its outcome source. So that is false alarm, false positive, false dismissal, or false negative, rate, speed, resources required, effects on environment, etc. That is, if a false positive result is acquired or false negative result is acquired, or the rates as well as the speed of the output solution acquired, as well as the resources required. Does it require more resources or less resources? Effect on the environment. What is the effect it produced? Those are the things that is included in rationality. So let's move forward to the next section, that is autonomy. Autonomy. A system is autonomous to the extent that its own behavior is determined by its own experience. That is, it is a self-made system. Like it can do whatever it want to do. If a problem is given, it finds the solution its own based on its own acquired experience or experience that is acquired by previous solutions that have been solved by it. Therefore, a system is not autonomous if it is guided by its designer according to a priori decision. That is, if a designer already set up a code through which the system is working, it is not autonomy. The system or the intelligent agent is not acquired, has not acquired autonomy. To survive, agents must have. To survive autonomy, the intelligent agent must have enough built-in knowledge to survive, the ability to learn. That is, it must have an intelligent agent to acquire autonomy. It must have already built-in knowledge that can survive any conditions, any problems it has to face, as well as it must have the ability to learn. It must have more training data available. Whether in the case where the designer provide training set, that system doesn't acquire autonomy, while the system itself has the ability to acquire training data and autonomy can be acquired. Okay, next section includes some agent types. So we have been talking about intelligent agents and rationality as well as autonomy. So let's look forward to some agent types. What are the different agent types? So some of the agent types mentioned here are table-driven agents, simple reflex agents, agents with memory, agents with goals, utility-based agents. Okay, what do you mean by table-based agents? Use a percept sequence or action table in memory to find the next action. They are implemented by a large lookup table. Okay, here a large table, right? Rows and columns. That's a form of memory location. And here all the sequence of actions are provided, and it automatically look forward for the next actions that must be performed, and it is implemented, and they are implemented by a large lookup table. Lookup table is it is known as lookup table. Okay, next a simple reflex agent are based on condition action rule implemented with an appropriate production system. They are stateless devices which don't have memory of the past world states. Okay, here they are based on condition action rules, and they are implemented with the appropriate production system, and they are stateless devices. They don't have states and don't have memory of the past world states. They don't have any knowledge about the past world states. And the next point is agents with memory. Okay, they have internal state which is used to keep track of the past states of the world. They have knowledge about the past states of the world, right? They have internal states and have past knowledge about the world. Agents with goals are agents that, in addition to state information, have goal information that describes desirable situations. Agents of this kind take future events into consideration. Okay, in this case, it have state information as well as goal information, so it can take actions in consideration for the future events that can occur. Okay, so it can produce desirable solutions for the situations. Okay, next is utility based agents. Based, they are making the decisions on classic axiomatic utility theory in order to act rationally. They can make decision on classic axiomatic utility theory in order to act rationally. Okay, they can act rationally. Unlike the systems mentioned above, these systems can act rationally with the help of classic axiomatic utility theory. Okay, in this section, we will be talking about all those agents mentioned in the previous lecture. Okay, first, table-driven or reflex agent architecture. Here we will be studying about the block diagram where an agent is provided as well as the environment. The environment is the outside and the agent is the inside functioning. Okay, a sensor is provided, and the sensor tells us about what the world is like now. And next step, it passes through the what action I should do, and it passes to the effectors. And here condition action rules are provided, and it communicates to the environment via sensors and effectors. And next step, we will be looking forward to table driven agents and in-depth details. So here, table lookup of percept action pairs mapping from every possible perceived state to the optimal actions for the state. Okay, table lookup of percept action pairs mapping from every possible perceived state to the optimal actions for the state. And the problems include are too big to generate and to store. Like chess has about 10 raised to 120 states, for example. Right here, we are using table-like structures to store memory, and if we want to store the data for a chess game, we want to store 10 raised to 120 states. It's a big data to store, right? And no knowledge of non-perceptual parts of the current state. We don't have the knowledge about or non-perceptual parts of the current state. Next point is not adaptive to changes in the environment. Requires entire table to be updated if changes occur. Okay, it is not adaptive. If a small change occur in the environment, we must update all the tables content, right? Next, looping. Can't make action conditional on previous actions or states. Like if a change occur in the previous state, we cannot change it. We can't change the actions conditional, right? It's just the problem stated here of the table driven agents. Next, here we'll be talking about simple reflex agents. Okay, the simple reflex agents are rule-based reasoning. Here, rule-based reasoning to map from percepts to optimal actions. Each rule handles a collection of perceived states. Okay, here optimal actions are produced from the mapped percepts. Okay, it still has some problems, even though it produces optimal actions that are still usually too big to generate and to store. Still usually too big to generate and store. They are too big to generate data and to store, as well as we don't have still no knowledge of no non-perceptual parts of the state. We don't have no knowledge about the non-perspective state of the states. As well as next point is still not adaptive of changes in the environment, requires collection of rules to be updated if changes occurs. Still can't make action conditional on previous state. Okay, it's similar to the previous state, right? They are similar. Table driven as well as simple reflex agents are similar, even though it produces optimal actions. So let's pass on to the next slide, that is architecture for an agent with memory. We are looking to agent with memory. Okay, here also we have agents as well as environment, and here is sensors which pass on to what the world is like. Here we can know about state, how the world evolves, what my actions do, and it pass on to what action I should do now. And here we use action, condition, action rules, and an effector is here, and the effector passes the action on to the environment, and it communicates with agent and environment through the sensors and effectors. So let's pass on to the next slide, and it is agent with memory details. Okay, encode internal state of the world to remember the past as contained in the earlier percepts. Okay, needed because sensors do not usually give the entire state of the world at each input. So perception of the environment is captured over time. State is used to encode different world states that generate the same immediate percepts. Requires ability to represent change in the world. One possibility is to represent just the latest state but then can't reason about hypothetical course of action. Example, Brooks's Subsumption Architecture. Okay, here internal state is encode of the world to remember the past as contained in the earlier percepts. Okay, and it has knowledge about the past state, and in needed because sensor do not usually gives entire state of the world. It doesn't in the sensor doesn't give the knowledge about the entire state of the world as the input. So the perception of environment is captured over the time. So the perception is captured over the time, and the state is used to encode different world states that generate the same immediate percepts, and require ability to represent change in the world. It must have the ability to represent change in the world, and the possibility is to represent just the later states but then can't reason about hypothetical course of action. It doesn't have the guarantee to reason about the hypothetical course of action. And here an example is given: Brooks's Subsumption Architecture. Okay, here we will be discussing about Brooks's Subsumption Architecture. Main idea here is it is build complex, intelligent robots by decomposing behaviors into a hierarchy of skills, each completely defining a complete percept action cycle for one very specific task. Example: avoiding contact, wandering, exploring, recognizing doorways, etc. Each behavior is modeled by a finite state machine with a few states, though each state may correspond to a complex function or module. Behavior are loosely coupled asynchronous interaction. In this session, we will be discussing about goal-based agents. Okay, here architecture for goal-based agent is shown. Okay, here is agent and environment. The agent consists of sensors, effectors, and other internal activities. So when a sensor senses and the environment, it will look out what the world is like now, what it will be like if I do an action A, and in the both condition consists of what is the state, how the world evolves, what my actions do, and it pass on to what action I should do now, and the goals involved is shown here. Then the effector perceives the conclusion or the solution and it's passed on to the environment. Next, we will be passing on to the next slide, that is goal-based agent. Okay, choose an action so as to achieve a given or computed goal. Okay, so goal can be given or it can be computed accordingly for each situation. Suppose certain condition can be given by the user itself, or the user doesn't know the solution for it and can be asked for the intelligent agent to compute what will be the solution, the best solution for it, and if the action is performed according to the intelligent agent. A goal is a description of a desirable situation. Okay, a situation, it is a description of a desirable situation. Means if a problem occurs and a desirable situation, or it must be like the solution must be like it, that is the condition stated here. Keeping track of the current state is often not enough. Need to add goals to decide which situation are good. Okay, keeping tracks of the current state is not enough. Even though we keep the track of the current situation, the solution for the goal that to be achieved is not enough. So we must need to add goals to decide which situation are good. We must analyze the best solution for it. Deliberative instead of reactive. It is deliberative. We are adding new goals to it rather than reactive. Right here, may have to consider a long sequence of possible actions before deciding if goal is achieved. Involves consideration of the future. What will happen if I do? That is the statement which must be used, right? If I do something right now, what will happen in the future? It must always consider what will happen in the future in mind. So let's pass on to the next session. In this section, we will be talking about architecture for a complete utility-based system. Okay, here we have agents and environment. And the sensor senses the environment and acquires the knowledge of the environment, and it passes on to what the world is like now, what it will be like if I do action A, how happy I will be in such a state. Okay, it includes what the state is like, how the world evolves, what my actions do, and the utility. What actions I should do now, and the final state is effector. And the effector percepts or gives out the actions to be performed onto the environment. Next, we will be passing to the next slide, that is utility-based agents. When there are multiple possible alternatives, how to decide which one is the best? A goal specifies a crude distinction between a happy and unhappy state, okay? But often need to be more general performance measures that describe degree of happiness. Utility function U colon state arrow reals, indicating a measure of success or happiness when at a given state, allows decision comparing choice between conflicting goals and choice between likelihood of success and importance of goals if achievement is uncertain. Okay? When there are multiple possible alternatives, we must decide which one is the best. A goal perceives or specifies which one is the best for the or which is happy and unhappy state, but often need more general performance to understand the degree of happiness. Here there will be conflict in the decision-making process, deciding whether the choice between likelihood of success and importance of goals. The achievement is uncertain in this case. Here utility is given more preference. Here the indication of a measure of success or happiness when it is given a state depends upon the utility. In this session, we will be talking about properties of environment, right? Fully observable, partially observable. These are the first point we will be looking into. Fully observable or partially observable. If an agent sensor gives it access to the complete state of the environment needed to choose an action, the environment is fully observable. Such environments are convenient since the agent is freed from the task of keeping track of the changes in the environment. Next, we will be passing to the next point, that is deterministic or stochastic. An environment is deterministic if the next state of the environment is completely determined by the current state of the environment and the action of the agent. In a stochastic environment, there are multiple unpredictable outcomes. In a fully observable deterministic environment, the agent need not deal with uncertainty. Okay. In fully observable environment, an agent sensor gives it access to the complete state of the environment, needed to choose an action, and the environment is fully observable, right? While in deterministic, if the next state of the environment is completely determined by the current state of the environment and the action of the agent is stochastic environment, there are multiple unpredictable outcomes. So, in a fully observable deterministic environment, the agent need not deal with uncertainty. No uncertainty can be seen in deterministic. So, the next properties of environment are episodic or sequential. An episodic environment means that subsequent episodes do not depend on what actions occurred in previous episodes. In episodic environment, here the previous episodes are not given preference, and the subsequent episode pass on without depending upon the previous episodes. Actions occurred in the previous episode. In a sequential environment, the agent engages in a series of connected episodes. Here, the agents engage in a state where each episodes are connected with each other, right? Such environment don't require the agent to plan ahead. Here, the agent doesn't require to plan ahead what to do in the next episodes or next state. Next point is static or dynamic. A static environment does not change while the agent is thinking. Doesn't change. The static environment doesn't change while the agent is thinking. The passage of time as an agent deliberates is irrelevant. The agent does not need to observe the world during the deliberation. The agent doesn't require to observe the environment, how it changes, what will happen, or something like that. Okay, in this session, here we'll be discussing about discrete or continuous, single agent or multi-agent. Discrete or continuous. If the number of distinct percepts and actions is limited, the environment is discrete, otherwise it is continuous. Here, the number of distinct percepts or actions are limited, they are discrete, otherwise they are continuous. Single agent or multi-agent. If the environment contains other intelligent agents, the agent need to concern about strategic, game theoretic aspects of the environment for either cooperative or competitive agent. Most engineering environments don't have multi-agent properties, whereas most social and economic systems get their complex from interactions of more or less rational agents. Next, here characteristics of environment is shown, where we will be discussing about solitaire, backgammon, driving, internet shopping, medical diagnosis. There is fully observable, deterministic, episodic, static, discrete, and single agent. Okay, let's look into it. Whether solitaire is fully observable? No, right? Deterministic? Yes, we can determine it. And it's episodic, right? And it's static, as well as it is discrete and it only has a single agent. So let's look forward on to the other games here. Okay, backgammon. It's also fully observable. It's not deterministic, and it is not episodic, but it's static and discrete, but it's not a single agent. While in the case of driving, is it fully observable? No, right? It's deterministic, right? No, it's not episodic as well as static or discrete or single agent. So let's look into the internet shopping. It's also not fully observable, not deterministic, not episodic, not static, while it's discrete, but it's not single agent. Let's look forward onto the medical diagnosis. Yeah, medical diagnosis is not fully observable, it's not deterministic, not episodic, not static, not discrete, but it is single agent. Lots of real world domain fall into the hardest one. It is the most hardest one, right? It is only has single agent, but doesn't follow other criterias. So the summary of all sessions we covered are: an agent perceives and acts in an environment, has an architecture, and is implemented by an agent program. Okay? An ideal agent always chooses action which maximizes its expected performance and gives its perceived sequence so forth. And an autonomous agent uses its own experience rather than built-in knowledge of the environment by the designer. An agent program maps from the percept to action and updates its internal state. Reflex agent responds immediately to percepts. Goal-based agent act in order to achieve the goal. Utility-based agents maximize their own utility function. Representing knowledge is important for successful agent design. The most challenging environments are partially observable, stochastic, sequential, dynamic, and continuous and contain multiple intelligent agents.